In this lecture, we'll use the linear combination of atomic orbitals method to derive the band structure in the general case when we have more than one atom in the unit cell and we're in more than one dimension. And to be specific and cut down on the number of indices and summations, we look at the example with 2 atoms per unit cell and point out the extension if we had more than 2 atoms, and we'll work in a general number of dimensions. And we'll proceed in the same way as we did in the simple case of a single one-dimensional chain of s orbitals, and write a trial wave function with coefficients which will vary to minimize the energy. So this time, our trial wave function is going to look like this. It's going to be labeled by quantum number k. It's going to be a function of r. And let's normalize it by 1 over the square root of the unit cells. And we'll sum over all of the unit cells. Of course, in a truly periodic infinite solid, n would go to infinity, but to keep the mathematics convenient, we'll make it finite. So n here is the number of unit cells, which will be very large. And our wave function has the block form, so it's e to the I k dot r sub n here, where r sub n is now any lattice vector. And within our unit cell, we have 2 atoms. And so we have a coefficient, C sub 1 of k, describing the contribution of orbital 1. And orbital 1 we'll describe by wave function phi 1, which is a function of r, and it's in the nth unit cell at some position d1 from the origin of that unit cell. And since atom 1 is not at the origin of its unit cell, we have to account for that in the block function by putting in an additional phase vector, e to the ik dot d1, because the position of atom 1 is r sub n plus d1. And then we have a second atom, which will give coefficient C2 of k, and we'll describe by wave function phi 2. It's a function of r. It's also in the nth unit cell, and it's at some position d2 within that unit cell. So it gets an extra phase vector, e to the ik dot d2. And of course, if we had more atoms, we'd have an extra coefficient and an extra local orbital wave function for each atom. So just to recap, phi 1 is the wave function describing atom 1 at position d1 in the nth unit cell. Phi 2 is atom 2 at position d2 in the nth unit cell. And these e to the I k dot d1 and e to the I k dot d2, these are the phase vectors describing the position of the atoms within the unit cell, whereas e to the ik dot r1 is the phase vector describing the overall position of the unit cell. And as before, when we apply the variational principle to the more simple case, we have here a sum over the atoms within the unit cell with coefficients that we want to determine. So if we sketch, for example, in one dimension, what our system looks like, here's our unit cell. And there's two atoms in the unit cell, atom 1 and atom 2. Atom 1 is at position D1, and atom 2 is at position D2. And of course, these repeat periodically in each unit cell. So if this, for example, is the nth unit cell, if the middle unit cell is the nth unit cell, then this position here is position R sub n. And so we see that atom 1 is at position R sub n plus D1, and atom 2 is at position R sub n plus D2, consistent with these phase vectors. Okay, so this is our trial wave function. And of course, what we want to solve is the Schrödinger equation, the Hamiltonian operator operating on psi sub k of r is equal to E sub k times psi sub k of r for the form of the wave function we just wrote down, in order to find the energy as a function of k. That's what we mean by the band structure, how the energy disperses with the k value, and the coefficients C1 and C2, which will give us the eigenfunctions, the wave functions at each k value. So here's our approach, what we're going to do. Will be to multiply both sides of the Schrödinger equation, this equation here, on the left-hand side, so pre-multiply both sides of the Schrödinger equation by first this factor, 1 over square root of n, the integral from m is equal to 1 to n, e to the minus I k dot r sub m. Notice I'm using a different index here in the summation so I don't mix up my indices. Phi 1 of r minus capital R sub m minus d1 e to the minus I k dot d1, and then integrate over all space. So I'll take h times the psi of k that we wrote on the previous page, multiply that on the left-hand side by this expression here, integrate over all space, and equate it to the right-hand side of the Schrodinger equation pre-multiplied by this expression and integrated over all space. And after a lot of rearranging and simplifying in mathematics, I'll end up with an equation which will turn out to be useful. Then we'll repeat the process again, pre-multiply both sides of the Schrodinger equation by a similar but slightly different expression, 1 over root n, sum over m is equal to 1 to n, e to the minus I k dot r sub m, this time phi 2 of r minus r sub m minus d2 in this case, e to the minus I k dot d2. Sorry, I forgot to put my complex conjugate sign up here. The wave function that we pre-multiply by is the complex conjugate. And then again, we'll integrate over all space and do a lot of simplification and get another equation. So this process will give us two equations which will depend on C1 and C2 and on the energy. And we'll solve these two equations in a matrix form. Okay, so what I'm going to do is skip first of all to the answer that we'll get if we did this process and integrated over all space, and just write down the equations, and then we'll look at what they mean and see what the band structures look like. And then at the end of the lecture, we'll go back and actually do this just for one case. It's the same for the other, so you can see in detail where it comes from. But so as not to detract from the physics, we'll go first just to the answer and work with it. Okay, so the result, when we do the pre-multiplication and integrate over all space, looks like this. We end up with two equations. The first one is alpha 1 C1 of k plus beta sum over all the nearest neighbors e to the I k dot the nearest neighbor distance times C2 of k is equal to E of k C1 of k. And I'll define these terms alpha 1 and beta in just a second. And the second case, when we pre-multiplied by the term with phi 2 in it and integrated, gives us alpha 2 C2 of k plus beta, the sum over the nearest neighbors, E to the minus, this case, I k dot nearest neighbor distance, C1 of k is equal to E of k C2 of k. And here our parameters, alpha 1, alpha 2, and beta. Make a list of these over here. Alpha 1 is equal to the integral phi 1 star h phi 1 over all space. So it's just the energy of an electron in atomic orbital phi 1. Alpha 2 is equal to the integral phi 2 star h phi 2 over all space. So it's just the energy of an electron in atomic orbital number 2. And beta is the cross term, the integral of phi 1 star h phi 2 over all space, which is equal, because h is Hermitian, to the integral of phi 2 star h phi 1 over all space, in the case where phi 1 and phi 2 are nearest neighbors. And otherwise, it's equal to 0. So the beta term represents the ability of the electron to move from wave function phi 1 to wave function phi 2. It's the bonding integral in the solid. Okay, so now let's solve these equations simultaneously in a matrix form. If you have another way that you like to solve such simultaneous equations, this is of course also completely fine, but this way is quite convenient. And let's introduce a little bit more notation. I'll put this over here. Let's write the sum, or write as g of k, the sum over all of the nearest neighbors, e to the I k dot, the nearest neighbor distance. So then our matrix has a particularly straightforward form: alpha 1, beta g of k, from these terms, alpha 2, beta g star of k, alpha 2, from these terms, the coefficient of C1 and the coefficient of C2, times the vector C1 of k, C2 of k, is equal to E of k, C1 of k, C2 of k. And so to solve for the energy, we just have to solve the secular determinant, alpha 1 minus E, beta g of k, beta g star of k, alpha 2 minus E, is equal to 0 to obtain the energies. So this secular determinant, of course, we can extend. If we have more atoms, we'd have then just a line with alpha 3 minus E, and so on. And so in general, we can use such a secular determinant to obtain the band structure, to obtain the energy as a function of k, which is very convenient. Okay, so let's then solve this to extract the energy. And so this is very straightforward. We have just expanding the determinant, alpha 1 minus E alpha 2 minus E minus beta squared, the square modulus of G of K squared is equal to 0, which gives us, with a little bit of rearranging, that the energy is alpha 1 plus alpha 2 over 2 plus or minus the square root of alpha 1 minus alpha 2 squared plus 4 beta squared, the square modulus of G of K squared, all over 2. So this is the general case when we have two atoms in the unit cell for any number of dimensions, whatever their connectivity, because the crystal structure, the connectivity between the atoms, is just captured in this G of K, which is e to the ik times the sum over the nearest neighbor spacing. So let's look at the limit that we already know the answer to. Look at the limit in which the atoms, the two atoms in the unit cell, are identical. So alpha 1 is equal to alpha 2 is equal to alpha, say, and equally spaced. A distance A apart, say, and we'll look at the case of one dimension. And so this is exactly the case of the 1D chain that we already looked at. And so we should get the same answer, even though this time we're considering that we have two atoms in the unit cell. The physical system is exactly the same as we looked at before. We see now that if our atoms are spaced a distance A apart, our unit cell has length 2A, and so our range of K values is now from minus pi, instead of minus pi over A, it's minus pi over 2A, through K is equal to 0 to pi over 2A, because we've doubled the size of our real space unit cell. So in reciprocal space, in K space, it's the range of K values is halved. Our nearest neighbor vectors, if we take one atom, say this one, then we have one atom which is a distance plus A from this atom, and another atom which is at a distance minus A from the atom. And so our energy, substituting into this general form, alpha 1 is equal to alpha 2, then the energy is just alpha plus or minus beta e to the I Ka plus e to the minus I Ka, which is equal to alpha plus or minus 2 beta cosine Ka. So this quantity here, the e to the Ika plus e to the minus Ika, this is just our G of K for this 1D chain of equally spaced atoms. So let's sketch then this energy as a function of k, and our k values now range from pi over 2a through 0 to minus pi over 2a, and our cosine function, let's mark alpha here, our cosine function looks like this. Where this distance is 2 beta, so you notice that we have two bands, which is two energy bands, which is consistent with having 2 atoms per unit cell. Our bandwidth is 4 beta, as we obtained previously for the 1D chain. And instead of the bands running from k is equal to pi over a to k is equal to minus pi over a, they're folded back within the smaller range of k space because of the way we constructed the problem with the doubled unit cell. And so the region of the band structure within the simple 1 atom per unit cell, 1-dimensional case, lay between pi over 2a and pi over a, is now back between minus pi over 2a and 0. And likewise, the region of the band structure that would have been between minus pi over 2a and minus pi over a is mapped back into the region between 0 and pi over 2a. So this back folding has not introduced any new physics, it's just a different way of representing the band structure in the case where we have twice as many atoms in the unit cell. If we want to obtain the coefficients, we can substitute the energies back into the matrix equation to obtain C1 and C2. We'd have to substitute the energy at a particular K, and then we could solve and get C1 and C2 at that K. And if we did that, we would find that K is equal to 0 for the low energy bonding orbital, we would get C1 is equal to C2, and for the high energy antibonding orbital, we get C1 is equal to minus C2, as before. Okay, I want to look at one more example of, or I want to plot one more incidence of this equation, the energy as a function of k, for a slightly more complicated case where it actually really makes sense to use the 2-atom unit cell. One could argue that for this particular case, we just go back to the single atom per unit cell case, and then the whole problem is much more straightforward. But let's take one more example. Of alpha 1 being unequal to alpha 2, where the 2 atoms in the unit cell really are different. They can also be differently spaced. So our material may look something like this, for example. And we might have an example of 2 different atoms. each with a different s orbital. I'm choosing s orbitals in both cases so that the sign of beta is unchanged from the previous example. And this time, if I plot the energy as a function of k, from k is equal to minus pi over 2a through k is equal to 0 to k is equal to pi over 2a. And of course, this time, the unit cell length really is 2a. I can't reduce it by saying, okay, my two atoms are equivalent, because they're not. Then let's put alpha 1 plus alpha 2 over 2 here. And this time my band structure looks like this, where the energy at pi over 2a is alpha 1 for the lowest band and alpha 2 for the higher energy band. So we see that our band structure is different in this case, and significantly, it should be symmetric between 0 and pi over 2a and 0 and minus pi over 2a. That's just my bad drawing. Most noticeably, we now have a band gap, an additional band gap at k is equal to plus or minus pi over 2a, whose size is determined by the energy difference between atoms 1 and atoms 2. The most bonding orbital is still at k is equal to 0. So down here, we have C1 is equal to C2, and this is our bonding orbital. And the most anti-bonding orbital has C1 equal to minus C2. And the orbitals at the edges of the Brillouin zone at plus or minus pi over 2a, these have the energies of the isolated atoms, and so they correspond to non-bonding orbitals because the energies are unchanged from the isolated atoms. I want to just change what I said here and say that the antibonding orbital C1 and C2 have opposite sign, and for the bonding orbital C1 and C2 have the same sign, because in the case where the two atoms are different, the magnitudes of the coefficients are not necessarily equal. Okay, so that's the end of the physics part. What I want to do to finish off is this detailed derivation for the pre-multiplication and the integral for those of you who really enjoy the mathematics, to see where it comes from. And so if you're only interested in the kind of physics part, then you can stop here. But if you want to see the detailed derivation, then we'll quickly finish. finish with that. And first I want to remind you of some notation, or introduce you some notation if it's not familiar to you, that the integral of phi I star phi j over all space, we're going to write in what's called matrix notation as this inner product symbol between phi I and phi j. And the integral of phi I star times some operator, phi j over all space, we'll write with this notation, and this is purely just for convenience to stop us having to write out a lot of integrals. And then within this notation, we're going to make use of some results from symmetry and orthonormality. So this is just some notation. Then we're going to use the fact that if phi 1 is in the same unit cell as the next phi 1, then its integral of phi 1 star phi 1 over all space is equal to 1. If we're looking at two phi 1 orbitals in different unit cells, then these two atomic orbitals are actually different from each other, and this integral will be 0. So if the phi 1s are in different unit cells, then this integral is going to be 0. In all cases, the integral over phi 1 times phi 2 is going to be 0 because we assume that they're orthogonal. And then for the energies, the integral of phi 1 times the Hamiltonian times phi 1 is equal to alpha 1, again, if the phi 1s are in the same unit cell. And it's equal to 0 otherwise. And the same for phi 2. This will be alpha 2 if we're talking about the phi 2 on either side of the integral being in the same unit cell, so it's the same wave function, or it's equal to 0 otherwise. And then the last one, phi 1 h phi 2, which is equal to phi 2 h phi 1 is equal to beta for phi 1 and phi 2 nearest neighbors, or it's equal to 0 otherwise. Okay, so we'll make use of all of those terms, and let's now do the pre-multiplication and integral. So we're going to multiply the Schrödinger equation by 1 over root n, sim over m is equal to 1 to n, e to the minus I k dot r sub m, e to the minus I k dot d1, phi 1 star r minus r sub m minus d1. And the trickiest thing here is to keep track of all of the terms and not mess up. So this is going to give us then, on the left-hand side, 1 over n, because we had already a root n and now we've got another root n. We're going to have a double sum over m is equal to 1 to n and n is equal to 1 to n, e to the I k dot r sub n minus r sub m. And now our atomic orbital coefficients, c sub 1 of k, e to the I k dot d1 minus d1 from here. And then our integral phi1 r minus r sub m minus d1 times the Hamiltonian operator times phi1 r minus rn minus d1. So that's the term from the first atom. We'll come back and simplify it in a moment. Let's write down the term from the second atom. So plus C2 of k e to the I k dot. This time we have d2 minus d1. And then our integral is phi1 r minus r sub m minus d1 h phi2 of r minus r sub n minus d2. Okay, hopefully I haven't made any mistakes. So what can we simplify? Well, this first e to the I k dot d1 minus d1, that's an easy one. It's e to the I k 0, so this gives us a 1. The integral with both phi1 terms in it, this is equal to alpha 1 when the two phi1s are in the same unit cell. So that's when r sub m is equal to r sub n. Otherwise it's 0. And we have a double sum over m and n. And so r sub m is equal to r sub n times. So this will give us n times alpha 1 when we do the double summation. The second integral, the one that's between phi1 and phi2, this gives us a beta when phi1 and phi2 are nearest neighbors. And this happens twice. So we have nearest neighbors first of all when m is equal to n, then phi1 and phi2 are in the same unit cell and are nearest neighbors. And this happens n times. And it gives us in our exponent an e to the I k dot the nearest neighbor distance, where we're looking at the nearest neighbor distance within the unit cell here. We also have nearest neighbors. It's the first case. Second case where we have nearest neighbors is when n minus m is equal to 1, and this also occurs n times in our double summation. And this gives us an e to the I k times the nearest neighbor distance, where we're now looking at this nearest neighbor distance here. So this is a little bit complicated to visualize geometrically, but you can convince yourself that this is correct. The other combination that you might think will work but actually doesn't would be when we have m minus n is equal to 1. And in that case, we would be looking at atom 1 here with atom 2 here, and these would not then be nearest neighbors. So these are really the only two cases where phi 1 and phi 2 are nearest neighbors. Okay, so then we can simplify our left-hand side of the equation that's pre-multiplied by this left-hand side of the Schrodinger equation pre-multiplied by this term integrated over all space, and we obtain alpha 1 C1 of k plus beta times the sum over the nearest neighbors e to the I k dot d nearest neighbor C2 of k. Phew, okay, so that's the left-hand side of the Schrodinger equation. The right-hand side is a bit more straightforward. Again, we have 1 over n, sum over m is equal to 1 to n, sum over n is equal to 1 to n, e to the I k dot r sub n minus r sub m, C1 of k, phi 1 r minus r sub m minus d1, e of k, and this is going to be more straightforward because of course e of k is just a constant, phi 1 r minus r sub n minus d1, and the second term, C2 of k, e to the I k dot d2 minus d1, phi 1 of r minus r sub m minus d1, phi 2 of r minus r sub n minus d2. Okay, so let's simplify this equation. Oh, and by the way, I didn't write out, we could have also put in here e to the I k dot d1 minus d1 as up here, but I set that to 1 straight away. Okay, so we can immediately simplify things in the second term because this last integral is between phi 1 and phi 2, and because of the orthogonality, this goes to 0, and so the second term is 0. Our e of k is just a constant, so this we can take out all the way to the beginning, and so we're left with just the integral between phi 1 and phi 1, and this we said already was equal to 1 when phi 1 is the same as itself, it's in the same unit cell, so when Rm is equal to Rn, which happens n times. So the left-hand side then is much more simple, and also when Rm is equal to Rn, then e to the Ik dot Rn minus Rm is just equal to 1. So our right-hand side simplifies to just e of k, c1 of k. So overall, our first of our two simultaneous equations is alpha 1 c1 of k plus beta, sum over the nearest neighbors, e to the I k dot the nearest neighbor spacing, c2 of k is equal to e of k, c1 of k. Phew. If you have a tremendous amount of stamina, you can repeat the procedure for the second case, pre-multiplying on the left by the this analogous term, but with phi 2 star in it, and you should get the second of the two simultaneous equations we wrote down yesterday. If you don't have the stamina to do that, I sympathize completely, and we're done.